Assalamualaikum everyone. Today, Expert Team B, which comprises of DT22 and DT31, will be presenting about pumps and motors for our peer teaching notes. So this is the slide overview of what we'll be presenting. So first we'll be presenting about the concept and theory. Then we also have the characteristics of pump operation, the mechanical design, the costing, implementation, and we also have examples for mechanical drawings, and that's all. So what is a pump? A pump is a device used to move a liquid from one location to another. So usually how we use a pump is we want to use the pump to increase pressure from lower region to a high region. So pumps are widely used in the oil and gas, chemical processing, waste treatment industry, and so on. So these are some of the types of pumps that we'll be looking into. First is the centrifugal pump. Next is the positive displacement pump, and lastly, which is the axial flow pump. So the net result of the pumping action may be to increase the elevation, velocity, and/or pressure of the liquid. However, in most process applications, pumps are designed to increase the pressure of the liquid. In that case, the power required is as follows. W equals to Fv times with the pressure change, where W is the power, F is the flow rate, V is the molar volume, and of course, change in P is the pressure change. So now we'll be talking about the characteristics of the pump operation. So first, we have the capacity, which is the flow rate of the fluid being pumped. So in this case, it may be mass flow rate, molar flow rate, or volumetric flow rate. So now we'll be talking about another characteristic of the pump operation, which is the pump head. So the head or the pump head, H, refers to the increase in total head across the pump, from the suction, which is S, to the discharge, D, where the head is the sum of the velocity head, static head, and pressure head. As you can see from the equation, V is for average velocity of liquid, Z is the elevation, P is the pressure of liquid, G is the gravitational acceleration, and also finally the liquid density. So now we'll be looking at the schematic of a pump. So a centrifugal pump consists of an impeller mounted on a shaft and containing a number of blades rotating within a stationary casing that is provided with an inlet and outlet for the liquid being pumped. Power, usually from an electric motor, rotates the shaft, which rotates the impeller. The rotating blades reduce the pressure at the inlet or the eye of the impeller, causing liquid to enter the impeller from the suction of the pump. This liquid is forced outward along the blades and to the blade tips at an increasing velocity. So now at this point, the liquid has acquired an increased velocity head from the power input of the pump. The velocity head is then reduced and converted to a pressure head as the liquid passes into the chamber with the casing and beyond the blades, and the pump is then discharged. So now we'll be looking at the characteristic curves. So when a centrifugal pump is installed in a pumping system and operated at a particular rotational rate, usually 1750 to 3500 RPM, the flow rate can be varied by changing the opening on a valve located in the pump discharge line. The pump head decreases with increasing flow rate while the brake horsepower increases with increasing flow rate. So this is the pump efficiency passes through a maximum. The pump will only operate at certain points on the characteristic curves. So for a particular pumping task, the required head volumetric flow rate point must lie somewhat below the characteristic curves as seen. So now we'll be talking about another characteristic curves, whereby the characteristic curves moves upwards with increasing impeller diameter. As shown, when a characteristic curve for just one rotation rate or impeller diameter is available, the approximate characteristic curve is desired for another rotation rate or impeller diameter. The affinity laws for a centrifugal pump can be applied. So as you can see in the following characteristic curves, for a given centrifugal pump, the characteristic curves moves upwards with increasing rate of rotation and the characteristic curves move upwards with increasing impeller diameter. So for centrifugal pumps, it operates at a high rates of rotation, and the imparted high liquid velocities can lower the local pressure, which will in turn make cavitation occur. To avoid cavitation, the available NPSH must be greater than the manufacturer's value for the required NPSH. So what I'm trying to say is if that pressure falls below the vapor pressure of the liquid, vaporization will produce bubbles that may collapse violently against surfaces where a higher pressure exists, which is a phenomenon called cavitation. So by lowering the efficiency and flow rate, the pump may be damaged. The tendency for cavitation is measured by a quantity particular to each pump and available from the manufacturer called required NPSH, which is net positive suction head, defined as the difference between the liquid pressure at the pump inlet and the vapor pressure of the liquid expressed as a head. So for the centrifugal pumps are limited by the rate of rotation of the impeller to the pump head they can achieve in a single stage. Typically, a maximum head for a single stage is around 500 feet.
In this slide, I explain the step to calculate for mechanical design for pump and motor. And in this part, we also learn a step to select a suitable pump for certain application. The first step to calculate pump mechanical design is to determine pump flow rate in gallon per minute, Q, and preferably in unit gallon per minute. Second step is calculate pump head using pump head formula. And as we can see, Z is elevation, V is velocity, P is pressure, and rho is the density of the fluid. And step 3 is to determine the size factor of pump, S, using formula S equal to Q multiplied by H power of 0.5. Step 4 is by determining Q and H, we can decide which pump we could use for our own application. And usually, a centrifugal pump could be selected because it satisfies the consideration of pump requirement, in which the volumetric flow rate Q is within 10 to 5,000 gallon per minute, and pump head is within 30 to 3,200 feet. Continuity from the last slide. Step 5, determine the pump efficiency using the formula below the step 5 box. And then determine brake horsepower for formula PB. PB is equal to Q H rho over 33,000 efficiency of pump. And step 7, determine motor efficiency and range for brake horsepower should be between 1 to 1,500 horsepower. And lastly, step 8, determine the power consumption of the motor and pump.
Okay, so I will show calculation of costing for pump first, step by step. Step 1, we need to calculate for base score, which is CB, by using this formula. Next, based on pump head that we calculate before, we need to determine number of stages and type of factor from table 16.20. Step 3, determine factor of material construction, which is FM. Characteristic of material construction can refer from appendix 3 first, and then to determine FM can refer from table 16.21. The last step, we need to calculate FOB purchase cost, which is a CP, by using that formula. For costing for motor, basically the steps are just same with costing for pump, but there is slightly different with the formula and so on. So step 1, we need to calculate base cost CP by using that formula. Step 2, we need to choose FT factor from table 16.22. And the last step, we need to calculate FOB purchase using this formula. That's how we calculate costing for pump and motor.
For example, mechanical drawing for pump and motor. Mechanical drawing for centrifugal pump, this is the front view and the side view. And this is the top view.
This is a mechanical drawing for centrifugal pump with the base. This slide shows about the cross-section of the centrifugal pump. This is the base of the centrifugal pump.
So the next one is gonna be the mechanical drawing for the electric motor, and we have 3 sides that is gonna be viewed in this section. And the first side is gonna be the front view, and also we have some dimension label in the AutoCAD drawing, as you can see in the slide. And the next one is gonna be the side view, also the same. We have some measurement that showing the dimension in the drawing. And And this is the final side, which is the top view. As usual, there are just some dimension label at the drawing so that we can see clearly about the measurement that is being shown.
Hello everyone, my name is Bara. I'm from DC31, and in today's video, we are going to explain to you about the spreadsheet that we have created to help you for the calculation and selection of the pump and motors and the costing calculation as well. So, as you can see, this is the interface of the spreadsheet. In every tab, you will find a table that will have input by you as the user, and this is the output in the orange color. Okay, and there are 5 tabs. The first one is pump selection. The second one is centrifugal pump costing. The third one is electric motors costing. The fourth one is external pump costing. The fifth one and last one is reciprocating plunger pump costing. So we have the first tab to select your pump, and the rest of the tab is to calculate the costing of the pump depending on the type. Okay, so starting off, we have listed down for you the advantages and limitations of the centrifugal pump. The main reason behind this is because centrifugal pumps are mainly used for 90% of the industrial processes, and you may consider using centrifugal pumps directly unless the limitations are exceeded and your specifications are much beyond the limitations. And on the right here, we have the criteria table that is also extracted from either book. So as you can see, for the centrifugal pump, it can handle up to 15,000 gallons per minute, and if more than that, it can even handle but with more than one centrifugal pump. While for the external gear pump, it's actually suitable for the higher dynamic viscosity. It can handle up to 500,000 centimeters, but take note that it's gonna be around 50% efficiency only. While for the reciprocating plunger pumps, it's actually mainly for the very high pump heads requirement that is not being able to handle by the external gear pumps or the centrifugal pumps. And take note that the price is increasing from the centrifugal pump. The external pumps are more expensive, and the reciprocating plunger pumps are usually more expensive as well. So this tab will help you in suggesting the suitable pump type for you based on specific input that will require you according to the criteria here. Basically, it will calculate the flow rate in gallon per minute because flow rate is actually an input. And then it will calculate the pump head, which is one of the main requirements for the pump selection. And lastly is the pump suggestion actually. And in the pump suggestion, we use an if formula. So for the if formula, it can, with the if cal formula, it can suggest for you. Okay, so let's start with a few examples that will show how it can suggest. So the first time we can try with 0.1 meter cube per second, and then for the pressure difference we can try with 3 atm, 5 for the initial velocity, and 25 feet per second for the final velocity. For the liquid elevation, we keep it at 200 meters, and the liquid density as 1500. And then for the kinematic viscosity, so since it has low kinematic viscosity, below 100, and the pump head is around 250, so it will suggest you the centrifugal pump. Okay? While if we try to decrease a bit or the flow rate to 0.032, and then we keep the pressure difference the same, but we try to increase the head basically by increasing the velocity, and also we can just increase the velocity. This now we increase the pump already, and we can increase also the kinematic viscosity, which is more than 100. We can increase it to 200,000. After this, it will suggest you the external gear pumps, because the external gear pumps can handle up to 500,000 centistocks of kinematic viscosity, while centrifugal pumps cannot handle this kind of kinematic viscosity anymore. So for high viscous pumps, it can be handled by the external gear pumps. But how about we try to increase the pump head while decreasing the growth for the canvas viscosity? So let's keep the canvas viscosity at 50,000 while increasing the pump head. We make the pressure difference at 10 atm, and then the velocity to 300, and then the liquid elevating to 500. As you can see, it will directly suggest you the reciprocating Van Bergen pump because the pump head is actually very high and it cannot be handled by either the centrifugal pump or the centrifugal pump. And this is how the pump selection works. And take note that this is just a system depending on calculation only it will suggest, while you need to have the understanding of the criteria and also the limitations of the centrifugal pump to be able to select. After this, let's say we start with the centrifugal pump first. So maybe we can use the same numbers from just now that suggested as the centrifugal pump: 0.127, 3 atm, 5 to 25 meter per second, 200 elevation, and 1500 density. Okay, so basically those inputs are very important because it will usually calculate the pump head, which is a very important criteria and very important calculation that will help us in the costing calculation later on as well. So after this, you have additional criteria for the centrifugal pump. So for the centrifugal pump, one of the most important factors is the material of construction. So you have wide range of materials from cast iron to titanium, and it will help you in calculating the material factor. Okay, so different materials will cost you differently because of the price. So let's say we want to go with the cast iron, and then from here we can basically see from this table. You need to refer to this table to be able to calculate for the type factor. Okay, so let's say I go with the 2 impellers, or number of stages is the impellers. So you need to follow the table basically. For the shaft rate, it will be 3,600, and then the case plate orientation, it will be horizontal split case, HSC. For the flow rate range, it will be 50 to 1,100, okay, according to the table. As for the pump head range, 300 to 100,000, 1,100. Okay, and lastly is the maximum motor HP. Basically, it's 250. Okay, so as you can see, after we put this, the type factor is calculated, the material factor is calculated according to the material, and the base cost is calculated. After this, all the things are multiplied, and this is the FOB purchasing cost for the centrifugal pump, which is $58,000.
Good day everyone, my name is Neil Charlton. I'm from TT22. So I will continue to present on electric motors purchasing cost. First of all, we need to insert the value at the user input part, which is the pump specification. So let's say we put 0.06 meter cube per second for volumetric flow rate. It will directly give us the volumetric flow rate at gallons per minute and also the pump efficiency. Let's say the pressure difference is at 25 atm. The initial average velocity of liquid V1 at 1 meter per second, V2 at 50 meter per second, liquid elevation at 3 meter, and the liquid density at 2,500 kg per meter cube. Then we will get the pump head, the pump brake horsepower, motor efficiency, and also the power consumption base cost. So we can see from here the power consumption is at 400.16 HP. So from here, we need to refer to the table 16.22, which is the type motor enclosure. So we can see that only open drip-proof enclosure is from 1 to 700 HP, which totally enclosed fan cool and explosion-proof enclosure, their maximum HP is only 250. So from here we know that the type of motor enclosure here is open drip-proof enclosure. Then let's say the shaft rate of rotation is at 3600 RPM. Then we will get the FOB purchase cost. So how to differentiate between the totally enclosed fan cool and also explosion-proof enclosure? We need to consider the definition beside the table. So apart from that, if the pump brake horsepower is given, let's say it is 500 bhp, we will get the FOB purchase cost as well. So let's move to the external gear pump costing. Same as electric motor costing, we need to input the value at volumetric flow rate first. So let's input it at 0.05 meter cube per second. There we will get the volumetric flow rate at 792.52 gallons per minute, and also the base cost. After that, we need to choose the material of construction. Let's say we choose stainless steel. Then from the table, the material factor FM is at 2. So directly we will get the FOB purchase cost here. That's all from me. Thank you.
Assalamualaikum and hello everyone. My name is Mama Amir Asfar from DT22 and from Expert Team B31. So today I will do a demo for how to do a purchasing cost for reciprocating plunger pumps. So as you can see that from the left, there is a user input for the pump specifications, and from the right, there's an output that user will notify. So first, user need to input the value for volumetric flow rate in meter cube per second. So if we choose the volumetric flow rate value is 0.05, so it will give the output value of the volumetric flow rate in gallon per minute, which is 792.52. Take note that the volumetric flow rate to calculate the pump efficiency must apply over the range of 50 to 5000 gallon per minute. So if the volumetric flow rate is not placed into the range, kindly input the volumetric flow rate again. So back to the original one, if we choose the volumetric flow rate is 0.08 for example, so it will calculate the volumetric flow rate output in gallon per minute is 1268.03. So next, user need to input the value for pressure difference, for example 2. The initial average velocity of liquid is 1. Then the final average velocity of liquid is 50. So next is the liquid elevation in meter. For example, we choose 8 meter, and the liquid density is 45. So it will, from this value, it will calculate the value for pump head, which is 594.43, and the value for pump brake horsepower in brake horsepower value, which is 21.53. And next, it will calculate the base cost. So next, the user need to input the value from this below, which is the material construction, number of stages, shaft rate, KSP orientation, flow rate range, pump head range, and maximum motor head speed. Take note that all of this value must be referring to this table, which is table 16.2 and table 16.21. all the values are fixed and the user must be follow the value 100% to get the value for FOB purchase cost. Okay, for example, if the user choose the method of construction is cast iron, so if we can see that the output given is 1.0 for material factor, then you can see that here from table 16.21 the material factor for cast iron is 1.0. So user can input any material and it will give the value for material factor. So the next one is number of stages and so on. The user must follow every value from this table, which is table 16.2. So for example, user choose the number of stages is 1. The shaft RPM is 2600. Case speed orientation is vertical speed case. The flow rate range is 50 to 900. The pump head range is 50 to 400, and the maximum motor HP is 75. Then you can get the value for FOB purchase cost, which is 6,971.71. As I said before, user must follow 100% value from this table. So in case that the user wrongly input the value for maximum motor HP, which is 150, then the output will show that the user need to input the data again to get the purchase cost. So kindly refer the table. So back again to the original, which is 75. So the FOB purchase cost is given here. So if let's say that user want to change the nature of construction, the value will given here. Then any material construction you can choose to get the FOB purchase cost. Okay, for the last part, if the pump rate horsepower value is given, we can input here. Also noted that the value for pump rate horsepower must be in range of 1 to 200 because the reciprocating planar pumps can only afford this value to do a work. So if we choose the pump rate horsepower value is 150, then that said we calculate the value for FOB purchase cost.
Good day everyone, I'm Sarul Surantiaku from DD22, and now that you all have fully learned how to use our Excel tool, I will show you an example question. So firstly, you're tasked with selecting the appropriate pump for a chemical process that involves transporting acetone through a pipeline. This process requires a volumetric flow rate of 0.1 meter cube per second, a pressure difference of 2 atms, and involves acetone flowing from one tank to another. The initial velocity of the acetone V1 as it enters the pipeline is 3 meters per second, while the velocity at the outlet V2 is expected to be 20 meters per second. Additionally, there's an elevation difference of 35 meters between the two tanks, and the density of acetone is 784 kilograms per meter cube, and its kinematic viscosity is 0.41 centistones. Given these parameters, select the most suitable pump for this application. So to solve this question, we head on over to the Pump Selection tab and input the parameters that were given in the question. And from these parameters, the tool has suggested that we choose the centrifugal pump. Next, we move on to question number 2, where the selected centrifugal pump is made of stainless steel and equipped with a single impeller. Consider the priority of maintenance, accessibility, and ample space availability. Choose between HSE and VSE, which are the horizontal split case split case, and vertical split case. Determine the FOB cost of the pump. So we go to the centrifugal pump costing tab and input the parameters as before. Now, why we select stainless steel? Because of the corrosivity of acetone, where cheaper materials such as the ductile iron and cast iron are less suitable. And the difference between the HSE and the VSE is in the horizontal split case pump. The casing is split horizontally along the center line of the pump shaft, while in the vertical split case pump, the casing is split vertically, perpendicular to the ground. Horizontal split case pumps are often used in applications where space is not limited and maintenance accessibility is important, while the VSC pumps are commonly used in industrial and municipal applications where space constraints or installation requirements dictate a vertical orientation. So in this case, we select the HSG. And based on this table down here, and the observed gallon per minute flow rate and the pump head, the most suitable and cheapest option that we have is this fourth row, which is one stage and 1,800 RPM HSC with a flow rate of 250 to 5,000 gallons per minute, 50 to 500 range of the pump head, and lastly a maximum motor horsepower of 250. So based on this, we get an estimated cost of $49,986.64 for the pump. Next, we move on to question number 3, which is lastly for the electric motor selection of the pump. Considering the smaller size and the requirement for explosion-proof operation due to the flammable nature of acetone, choose between 3,600 RPM and 1,800 RPM and determine the FOB cost of the motor. So we head to the electric motor costing section and input the parameters from before. And we choose 1,800 RPM here because we choose 3,600 RPM here because the pump that we have selected here is actually a smaller pump, and in pump applications, lower speed motors, which is the 1,800 RPM, often preferred for larger pumps which require higher torque and slower operating speeds, while the 3,600 RPM is typically used for smaller pumps where space is limited and higher rotational speeds are acceptable. So select 3,600 here, and we choose the explosion-proof enclosure as acetone tends to combust. Vapor cloud mixture of acetone tends to combust at higher temperatures. And we get the FOB purchase cost of $5,574.29. And lastly, determine the final combined cost. So we just have to add the 49,000 and the 5,500. So that's all. Thank you for watching, and we hope that this tutorial has been useful for you.